We've been talking in multiplication of polynomials. Now we're going to go the opposite route. We're going to do factoring. Right? So we're going to start off, we're going to have probably about a week and a half shot of just nothing but factoring polynomials. Starting off easy with just reviewing greatest common factor. Real quick, let's look at that picture for a second. Okay, this explains what we've been doing and how that relates to what we're about to start doing. We've been doing the easy stuff in a way. I mean, we've been multiplying. We've been doing stuff like this. Take 3x times a polynomial. So really, I'm just multiplying two polynomials together. The first one only has one term, so it's a monomial. But we've done other stuff too. We've done multiple term polynomials times multiple term polynomials, right? We've done that stuff. We multiply those together and get one big polynomial. That's multiplication, right? That's the stuff we've been doing. When we start factoring, we just put that car in reverse and we do the opposite. Now we're going to start off with one big polynomial, and our job is to break that up into a product of factors of small polynomials that are equal to the big polynomial, right? Okay, so that's our goal. That's what we're going to do. We start off with greatest common factor stuff. This is just from the textbook, some stuff for your notes. Really, the thing I want you to know here, it's kind of important, is the difference between factors and terms. Factors are things that are multiplied. Terms in math are just things that are what? You tell me. No. Added or subtracted. Right? Factors, things that are multiplied. Terms are things that are added or subtracted. Okay. So let's start off with finding a GCF, greatest common factor. I've got three numbers. Well, what is the greatest common factor? Oh, no. I mean, just, I don't know what, don't give me the answer. Just in general, what does it mean?
The highest number that they all can be divided into.
Okay, that divides into all three numbers, right? So we want the biggest number that divides into all three of these numbers, right? Okay, normally that's not so hard to do if the numbers are small, but if the numbers are big, that's kind of tough, right? Just to come up with that number. So we might need to use like a factor tree, right? You guys remember factor trees?
Yes.
Okay, well, some do, some don't. Let's review this. What's a factor tree? So a factor tree is just it's a way we can organize factoring something, factoring a number in this case, right? When my factor tree branches, what do I have to write at the end of each branch?
It's like a circle. To write a circle around the biggest.
Say it again, numbers that multiply to 144, right? So there's a bunch of different combinations. In general, when we're writing out factor trees, it's helpful if we pick sort of medium-sized numbers and not like one really small and one really big number. Then we can prevent the tree from getting really long. So what would some medium-sized numbers be that multiply to 144?
Like 12 and 12?
12 and 12 would be perfect. We always want to look for perfect square factors if we can. It's not that big a deal now, but later on in the class, we're going to do some stuff where we specifically want to find, when we factor something, we want to find perfect square factors. That's helpful, right? That's the goal. So let's practice that now. Whenever we can, try to find perfect square factors. 12 and 12 works. Okay, and then I'm going to take each of those 12s and split those. So this 12 breaks up into
3 and 4.
And 3
is just 1.
So
right?
three. Okay, you guys circled them at the end, didn't you? I'm not going to do that, but you guys did. How come you circled it? What caused you to circle it?
So we can know which one was done.
Okay, yeah, it's the lowest you can go. So what do we call that factor then?
The lowest comes.
Least common.
No. starts with a P.
Prime.
Prime,
We got
yeah.
prime.
When we get down to a prime factor, we stop. Well, 4 can be factored down to 2 times 2, right?
Right.
So that one's done then. Those are all prime, aren't they? Okay. So 2 times 2 times 3. Well, we're doing a 12 again. I don't have to go through that whole process. I already know what the outcome's going to be. I'm going to get a 2 and a 2 and a 3. So we'll just cheat and do that. Right? Okay, 108. What is it? 12 and 9. Okay. Well, the 12 I already know. I just did it. So the 12, I'll cheat again. That's just 2, 2, and 3. What about the 9? 3 and 3. How about 210? It ends in a 0, so it's pretty easy.
Let's say 12. Oh,
No.
21 and 10.
21 and 10. There you go. 21 breaks up into
7
Seven
and
and
3.
10 breaks up
5 and
into
2.
Okay, and that's it, right? Those are all prime. Okay, so if I want to find the GCF then, well, the greatest common factor is the biggest thing that divides into all three of those evenly. Wouldn't the greatest common factor be built from all of the smaller factors that are common? Common means what? Like if you have a common room in a dorm, like a common kitchen, what's
They
that?
all
It's
have
just-
the same.
all have the same, right? Everybody would have access to it. So they all have the same. So let's underline what are the common factors of each of these, in each of these three strings.
2 and 3.
Okay, I've got a 3 in each. What else?
2.
2. Okay, got a 2 in each. Is there another 2?
No.
No. Another 3?
No.
God bless you.
Thank you. And the 5 and the 7 only show up in the third one, right? So that's it, just a 2 and a 3. So our GCF is just equal to 2 times 3, which is 6, right? Everybody agree? Yeah.
Wait, really? Use both by the 2? Oh, okay.
Right? Because the 2 and the 3 were the only factors that appeared in each of our trees. A single 2 and a single 3. Everything else, nothing else was common to all three. Give me thumbs. Does that make sense?
And so if there was a third, would you do like
Yeah,
2
we would.
times 3 times 4?
Yeah, or not. 4 would never be there because that's not prime.
Right.
But like, what if this tree had another 2 in it? Then we would have had 2 2s, right? That we could have contributed. But because this one only had 1, we only got to keep one of them.
Oh, I see what you mean.
See what I'm saying?
Oh.
Okay. All right. So now let's take this one step further. Well, this was a pretty inconvenient way. Like if I want to write this out, let's take this 144 and let's write this as a product of factors. So I could say 144 equals 2 times, how many 2's am I multiplying together? We're going to put them in order, increasing order. 2 times, 4 of them? And then 2 3's. Everybody see that? So there's 144 as a string of prime factors. Here's 108 as a string of prime factors. 108 is equal to 2 times 2 times 2 2's and 3 3's. And then 210
3 times 2.
is just that stuff, right? But in order. 2 times 3 times 5 times 7.
Oh.
And again, we see that the only ones that are common, I get a 2 common to each and a single 3 common to each, and that was it, right? Okay. Those are pretty inconvenient ways of writing out those big numbers though, right? What's a better way of saying all that stuff? What's a better way of saying 2 times 2 times 2 times 2?
2 to the 4.
2 to the 4.
2 to the 4 times 3 squared.
There you go. And 108
16 times equals 2 squared times 3 cubed.
There you go, times 3 cubed. And 210 actually just
That's
doesn't
just the way
change,
it
right?
is.
That's as simple as we can get it. 2 to the 1 times 3 to the 1 times 5 to the 1 times 7 to the 1. Okay, so now using that more efficient row, the green row is better than that brown row, right? Because it's shorter, much more efficient. How could I come up with my GCF from the green stuff? Same kind of thing. I still want to look for the kinds of factors that show up in all three numbers. Well, what were the kinds of factors that all three of them had?
2 and 3.
2 and 3, yeah. So we had 2 to some power times 3 to some power. We just need to figure out what the powers are. Well, let's look at the powers here. In the first case, we had, in the first case we had 2 to the 4th. The second case we had 2 squared. Third case we had 2 to the 1.
It's the lowest one.
It's the lowest one, exactly. Because isn't the 2 to the 4th contains a 2 to the 1 inside it, doesn't it?
Oh.
And 2 to the 3rd, 2 squared contains a 2 to the 1 inside it. But 2 to the 1 doesn't contain a 2 squared or a 2 to the 4th in it, right?
Right.
So does that make sense? So we're always going to take, if we have common factors, we can only take the smallest exponent in our GCF. Okay? So this needs to be,
Those. 1, 2.
no, it needs to be a 1, right? Because 1 was the smallest power of our common factor, right? How about the 3's? What's the smallest factor of 3 that shows up? 3 to the 1. So that also is going to be a 1. How about the 5's? Well, the 5 doesn't even count because we don't have 5's in those two, right? So we only have to worry about the 2 and the 3 because those were the common types of factors, right? Make sense? Okay? All right. So now let's look at finding the greatest common factor from a bunch of monomials. So these could include numbers and variables. Well, let's focus on the numbers first, or the variables first. Let's take this first example where there aren't even any numbers. What's the GCF of x cubed and x to the 7th? Well, x cubed is just x times x times x. X to the 7th is a string of 7 x's multiplied together. And so we can see when we write them as strings that we get 3 of those are common, but that's it. So my GCF is x times x times x, which is x cubed. But we don't want to go through that whole process. We're just going to look at the exponents. And we've got x's in both, but the smallest power of x is 3, so that's my GCF, right? So now you guys do this one for me. The greatest common factor of these two monomials, 6x to the 5th and 4x cubed. We can split this up, fortunately, into pieces. We can do the numbers first and the variables second, and just combine them in our GCF. Okay, so what about the number part? What's the GCF of 6 and 4? But what's the greatest common factor? I want to know what's the biggest number that divides into 6 and 4? 2. 2, you got it. So 2. And then what power of x would I include? Show me with your fingers. Yeah, good, x cubed, right? I can only take the smaller of the two powers, and so we get a 2x cubed. You got this, okay? All right, you guys try this one, please. Everyone just, if you want to, you probably need to go to a board, but just look at this and see if you can tell me here. What's going to be the greatest common factor? Is it going to, give me thumbs, will it include an A? Give me thumbs up or down. Yeah, it will, right? Don't all 3 of those terms have A's in them?
Yes.
Agreed? Give me thumbs. Is it going to include a B?
Yeah.
Yeah, they all include factors that have B's in them,
I
right?
said thumbs up, not voice up.
Okay, so now let's get exponents. What power of A would I include?
2. 2.
Yeah, right? The smallest of the common powers, right? Smallest is 2. What power of B? 2. Absolutely. Okay, so my GCF is A squared B squared, right? How come? Well, because if I wrote those all out as strings, the only common ones, I'd get 2 common A's and 2 common B's, and that's it. But don't do that. Just use the exponents. Okay, again, here's just a reminder. Notice that the GCF of terms containing variables will use the smallest exponent found among the individual terms for each variable, right? Which we already just decided. Okay, let's try this guy. Now we're going to go a step further. This time our goal is to actually factor this polynomial. So our goal is to write this as a greatest common factor times something else. Yes, sir?
3x.
Okay, so the greatest common factor, good, is 3x, right? The number part would be 3, everybody agree? And the biggest power of x would be x to the 1. Okay? All right, so now, you gotta really pay attention here. So if we wanna write this, if we wanna factor this polynomial, we're writing it as 3x times something else. Well, what about the something else? Okay, here's a good way to think about this. When I'm factoring out a GCF, what I'm really doing is I'm undistributing it from each of those terms. I've taken a 3x and I've undistributed it to put it out front, right? So if I want to know what goes here, here, and here, I could just think in terms of distribution. When I undistribute the 3x, that just means that if I were to turn around and redistribute it, I would have to get that, wouldn't I? So 3x times what would give me 6x cubed?
2x squared.
2x squared. There you go. So the first term is going to be a 2x squared. Okay, how about this one? 3x times what is negative 9x squared? Negative 3x. You got it. So easy, right? And then finally, 3x times what is 12x? 4. Okay, we got it. Make sense? Okay, now of course, if I multiply these together, I'm going to have to get out the original polynomial because that's what we just worked hard to undo, right? We worked hard to break the original polynomial into 2 factors. Agreed? Okay, so that's plan A. To me, I think that's almost the easiest way to do it.
Right.
But there's another way. Plan B is you can take the original GCF, which you guys found, no big deal, and then to find out what's left behind when I undistribute the 3x, all you have to do is just divide each term in the polynomial by the greatest common factor, right? So my GCF was 3x. If I take the 6x cubed and divide that by 3x, what do I get? Well, 6 over 3 is 2, and x cubed over x is x squared. Negative 9 over 3 is negative 3. X squared over x is x, right? How about this one? Look at this guy. The x's cancel. 12 over 3 is 4. Either way, doesn't matter. They do the same thing. Okay, give me 1 to 5 so far. How are we doing? Okay, need a little more practice. Okay, how about this guy? Everybody focus on this. Think about this for a second here.
I'm locked in.
First step is we got to come up with that GCF, right?
So negative.
7.
7. Okay, good. The number part 7. Everybody agree?
Yeah.
Okay, how about x's? What's the power of x?
X, and then there's straight line.
Just x to the 1, right? Because I only have an x to the 1 there. How about y? Just y. Y to the 1. Okay, so now, what's going to go down here? Let's see. Yeah, so how about this one? 7xy times what is 14x cubed y? 2x squared. That's it. Agreed? Or we could use the division method. We could look at it this way. Well, the y's cancel. 14 over 7 is 2. X cubed over x is x squared, right? Okay, how about here? 7xy times what is 7x squared y? X. Or just divide it. 7x squared y divided by our GCF. The 7's cancel, the y's cancel. X squared over x is x. Okay, how about this? 7xy times what is negative 7xy? Negative 1. Or again, now pay attention to this because this is a place where people make mistakes. The y's cancel, the x's cancel, and the 7's cancel. When stuff cancels vertically, does it equal 0 or 1?
0.
1. 1, right? When things cancel vertically, they equal 1. When things cancel horizontally, they equal 0. Here's what I mean. Like, watch this. Look at the difference. 2 plus negative 2 equals 0. Those cancel, right? when things cancel horizontally, they equal 0. But 2 divided by 2 equals what?
1.
1. When they cancel vertically, they equal 1. Okay. Give me 1 to 5 on that. How are we doing? 5 meaning great,
That's
1 meaning not so great.
I'm not good enough. That's a 5.
Okay, good. All right. Okay, what about this one? This is a little tricky.
Do we need to distribute?
No, we don't want to distribute. I mean, we could, but we don't really want it.
Be 2, obviously.
No.
Is it
Okay, to set you up for this, because you guys I can already see people are looking at this. They're not sure what to look at because this is not a polynomial, right?
No,
It's not really written in a polynomial form.
There's no solution.
No, it has a solution. But let's look at the original expression up here. I want you guys to show me with your fingers. Now, we said terms are things that are added or subtracted. Factors are things that are multiplied, right? I want to know when I look at this expression up here, how many terms are represented in that expression?
2.
3.
See, lots of different answers. The correct answer is 2. And here's why. Here's why. How many plus or minus signs do you see connecting things in that? Only 1. Now, these don't count. How come the pluses don't count? Because they're in parentheses, exactly. We only see 1 minus sign connecting 2 big things, right? I've got this big thing up here, that's term 1, and this big thing over there is term 2. Okay, now let's analyze the terms. Look at the first term. Show me with your fingers. How many factors are in the first term?
1.
2, because there are 2 things being multiplied. What's the first thing being multiplied?
6.
6. What's the second thing?
Why?
Right, and we got to start saying quantity. The quantity x plus 2, because it's in parentheses, right? So I've got 6 times the quantity x plus 2. So look at that. I've got the number of factors.
6 times x, that's also 6 times 2.
Right. There are my 2 factors. I've got a green factor and a blue factor. How about second term? How many factors? 2. Exactly. I've got the factor y, and I've got the factor x plus 2. Well, what do you notice about the factors?
Negative.
Do you see any common factors in the 2 terms?
Oh,
Yeah.
2. The same.
The x plus 2 is the same, isn't it, right? Aha, so there's, look at that. Yeah, the quantity, good. The quantity x plus 2 is the common factor. Everybody see that?
Yeah.
Okay, so now I want to know, that's my common factor that goes out front, my GCF. What's going to go in here? Well, look at this. You can just see it visually. Factoring out a GCF, I should have absolutely 100% attention here. You're going to miss something important. Eyes up here. Focus. See this. Like, take this in. If I factor out an x plus 2, if I undistribute that, what's left behind?
6 minus
y.
y.
How about that? 6 minus y. There you go. Right? So there it is. And if I want to, if I'm not seeing that, I can always you can always go back to the division process. If I take the first term divided by my GCF, it's pretty obvious that the x plus 2's are canceling, and I'm getting
Round, and the y round.
6. If I take the second term and I divide by my GCF, again, the x plus 2's cancel, and I just get a minus y. So what about one like this? Now, this is not a very hard one. If we write this out, let's write this as a product of, I'm going to tell you, like this is, I want the GCF out front, and I want everything else there. Okay, what about the power of a? Because I'm going to include an a, aren't I? A squared, my GCF would include an a squared. What about the number?
4.
Okay, so now here's the question. Here's the only question. Does the GCF, because this is not a hard one, but that poses a little question for us. Does the GCF include a negative or not?
No.
No.
Yes.
Yes.
Yeah.
If it's the highest, no matter what.
No, here's the rule. If the leading term is negative, then the greatest common factor is going to become negative. The greatest common factor is always going to have the same sign as the leading term. It inherits the sign from the leading term.
So like if 16 was in the front, then it would have been just positive. right?
Exactly, exactly. So because the leading term is negative, we're gonna make the GCF negative. Let's fill out the rest of it. Okay, what's gonna go there?
4a squared.
Negative
Or
4
2a.
a squared times what is negative 8a to the fourth? Positive
2a squared.
2a squared. Everybody agree? Okay.
Negative.
What goes here?
Negative 4.
Negative 4a squared times what is positive 16a cubed?
Negative 4a.
Negative 4A1.
Negative 4a. There you go, to the 1. And we wouldn't really write the 1, but it's there. And then
just
finally,
plus 2a.
negative 4a squared times what is negative 4a squared?
Plus 2. Or, yeah.
Boom. Okay. All right.
Oh yeah. Wait, why did I say 2?
Go to the board. Do that, please.
Because I was thinking of the a. I was thinking of the 8.
He was last.